You're coming down the home stretch in your thermodynamics class. The last few weeks you've spent analyzing cycles. Let's see, we've had steam power plant cycles, we've had internal combustion engine cycles, we've had Brayton cycles, the gas turbine engine model. You've had refrigeration and heat pump cycles. Wow, weeks and weeks of cycles. And now, as we move into chapter 12, we switch gears again, and we're going to be looking at processes that involve mixtures of ideal gases. So we're switching gears from cycles back into processes. So let's get started and see where you're going to be headed in chapter 12. This first part of chapter 12 is basically your roadmap. I'd like to give you an idea of what's going to be covered in chapter 12 from start to finish, and then a few introductory definitions. So this, of course, is the roadmap, and what I'd like to cover in this is the idea of mixtures, ideal gas mixtures, and something slightly different, mixing. And this chapter starts with ideal gas mixtures. And then really the most important, what I have found, the most powerful and important part in engineering when you're in manufacturing, when you're working in general engineering problems, you're working with atmospheric air, not just dry air, but atmospheric air all around us, air conditioning, heating, things like that, both in residential, commercial, industrial. So there's really two big parts of chapter 12. And this atmospheric air business, also called psychrometrics, is really a very important part of the chapter. But let's get started first. Let's just talk about dry air. You've had so many problems now in this class where air does this or air does this, air is compressed. And so you think about your own common sense, your own experience with breathing air, your high school and your college chemistry experience. Well, what is dry air in the first place? You know good and well that air is really a mixture of ideal gases, and primarily it's 78% nitrogen, 21% oxygen, and a little argon, a little CO2 that we breathe in air, and we exhale CO2 and the leftover nitrogen. So you recognize that dry air is mostly nitrogen and oxygen. And so as engineers, we use air so much in our engineering work, we treat it as a single unique substance, even though we know full well that it's a mixture of nitrogen and oxygen. So chapter 12, we're going to look at this mixture idea, but do recognize air, it's a mixture. And we use it so much that as engineers, we have built property tables that does the mixture analysis for you, so you don't have to do it every single time you have a engineering problem with air. So anyway, you see air, here's the molecular weight of air, 28.97. You fully understand where we get this 28.97. It's a mixture of nitrogen and oxygen and some other ideal gases. And in fact, we have thermodynamic property tables of dry air, table A22, that you've used a lot. In chapter 12, we're going to basically look at other ideal gases, mixtures of other ideal gases. So you can imagine in your head ideal gas constituent number 1 and constituent number 2 contained within a vessel, just like shown here on the slide. It could be nitrogen, could be oxygen, could be CO2, could be argon. You get the idea. So we're going to treat this mixture of ideal gases as a single ideal gas. But what we're going to do is we're going to need to figure out what is R of the mixture. And why would we want to do that? If we can figure out what the gas constant R of the mixture is, then we can go right back to what we're already familiar with, the fundamentals we're already familiar with, the ideal gas equation of state, PV equals mRT. And so that's what we're driving for, is we're not trying to throw totally new information at you. We're trying to get you thinking about the fundamentals and how can I compute R of some ideal gas mixture. Hopefully you visualize a path forward on how to do that, but it's still back to fundamentals. Those are mixtures. In other words, a constituent A, constituent B, constituent C, they're mixed within a vessel. Also in chapter 12, we're going to have problems associated with mixing ideal gas number 1 and ideal gas number 2, could be 3, 4, and 5, but we're going to mix unique ideal gases together in some kind of mixing chamber and come out with a mixture of 1 and 2. So do you see how that's different than a mixture? We're mixing. Now, this little sketch is a classic example of an irreversible process. I hope you remember from the middle of the course that we identified mixing as one of the features that would make a process irreversible. In other words, we couldn't reverse this process and put power in, reject heat, and reverse flows and exactly get the ideal gases 1 and 2 coming out the reverse end, okay? But I hope you recognize that this is nothing new to you. Do you see that this is a open system, steady state, steady flow? This control surface is not getting fatter or skinnier, steady state, steady flow. We've got 2 inlets and 1 outlet. So you know how to analyze this from your fundamentals. So remember the continuity equation. The mass flow rates are conserved. So that must mean that m dot of ideal gas 1 here must exactly equal m dot of ideal gas 1 here, and the same for gas 2. So do you see that mass has got to be conserved in this mixing process? Similarly, in the first law, do you see that you could apply the first law that you've already learned? Q dot in minus W dot out equals what? Steady state, steady flow. The sum of the M dot leaving, H leaving, minus the sum of the M dot in, H in. As long as you recognize that kinetic and potential energy changes are negligible here. So you've got this stuff in your mind. You've got these fundamentals in your mind. It's a matter of applying those fundamentals to mixing and mixtures. So that's the roadmap, and that's some introductory remarks about chapter 12. So can you think in your mind, what is a mixture? It's simply a couple of ideal gas constituents that are mixed together. What's mixing? You can take 2 or 3 or 4 constituents, mix them together in a steady state, steady flow manner, and get a mixture out. So what do they have in common? Ideal gas mixtures. Okay, well, I hope that brief introduction helps you get ready for chapter 12. And my main point here is the fundamentals you've already covered in this class, and now you're going to apply them simply to multiple ideal gas constituents.